All right, so I'll get started and try and catch up. So we're talking about hydrogen boron experiments with the DPF, but we're also going to be talking about some deuterium experiments. And I want to point out that our team has now been joined part-time at the moment by Sam Grund, who's our new research assistant, and he's only 29. So I think that perhaps is reassuring to Sunu, who's been worried about us all getting older. So the goal, of course, of our project is a 5 megawatt fusion generator based on hydrogen boron fuel. I think you guys are all familiar with what we're aiming for. So what I'm going to say this morning is talk about confirmation of theoretical predictions with the deuterium shots, our initial results running Decaborane, some problems, some solutions, and the next steps. So we've made a series of improvements. Last year, I already reported that we were getting higher currents up to 1.6 megamps with the dual switches. So having two switches on each capacitor, which reduced both the inductance and the resistance. A lot of the resistance in the circuit was coming from the switches. Second of all, we reprofiled the cathode so that from each tooth on the cathode, there was one filament. So we got higher current in each filament. Third, we introduced, after each shot, a cleaning shot with deuterium and nitrogen. And fourth, we increased the pre-ionization current up to 0.2 milliamps. The first thing we achieved was a much greater efficiency, almost double in the best shots, of transfer of energy into the plasmoid. So now we're getting 13% of the total capacitor bank to the plasmoid. The other major improvement that we had been looking for is that previously we had seen that the filaments that are shown in these earlier ICD images had been disrupted before they got to the end of the rundown, which is about 1800 nanoseconds. But as you see, by 1200, they were already completely destroyed. But now we got the first evidence in August that the filaments not only were surviving pretty strongly at 1000 nanoseconds, they survived all the way down to 1400 nanoseconds. And in these particular shots, where the pinch was at 1600 nanoseconds, they were reaching the end of the rundown. And you can see these two rather large filaments that are going off to the side. This is, we're looking at the gap between two cathode veins. So this is about 1 centimeter. And to review, our anode is 2.8 centimeters in radius. So that was a big achievement. The second thing was, with these improvements, we got confirmation of the optimal rundown velocity for deuterium. And in the process, we got a new record in fusion yield. So these are shots taken under the same conditions, with the exception of the difference between the blue and the orange, which I'll talk about in a second. So this is fusion yield in millijoules. A joule is approximately 10 to the 12th neutrons. So what we see is, as the rundown velocity increases, we have shots in a pretty narrow range going up to the predicted value. And then a pretty big drop. It dropped by almost a factor of 3 as you go to slower and slower velocities. Now, on top of that, interestingly enough, we found that there was a pretty big difference when we turned on the heating. We were using the heating to 70 C to vaporize the Decaborane, but we noticed that even when we were running with pure deuterium, the heating made a difference, quite a considerable difference. And you see the orange dots are without heating, everything else the same, and the blue dots are with heating. We don't have a theoretical explanation for this. I'd be interested to see whether any of you do. So the theory that I developed back in '86 derived from first principles the optimal velocities for filament formation. And it's this very simple formula, which is V equals the ratio of the electron mass over the ion mass times the velocity of light. So that comes out for deuterium to 8.2 centimeters per microsecond. And the velocity, the mean rundown velocity that we observed with that very sharp peak in yield was 4.1 centimeters per microsecond. And people are aware that in general, the peak velocity is very close to twice the mean rundown velocity. Now, this velocity was considerably lower than the alphane velocity for the conditions that we achieved this optimal rundown velocity. So again, it'll be interesting whether anyone can derive theoretically the ratio between the achieved velocity and the alphane velocity at the peak of the current. So by optimizing velocity, we were able to double the fusion yield. And with the heating, there was an additional 1.6. So between these two effects, we basically tripled the yield. Our videos come out of LPPFusion's research in fusion energy, the energy which will power a future of abundance for all, with a sustainable economy and a clean environment. Goods, housing, and transportation will be affordable to all once fusion kicks in. Fusion energy is the key to building a better world now. Support fusion research, $10 a month at lppfusion.com/support. The link is in the description. Thanks. We got a new record yield of 0.26 joules, or very close to 2.6 times 10 to the 11th. And that wasn't a big increase from our record back in 2017. But as you could see from the diagram, we were getting very consistent results. We were only getting a 25% yield variation, and there was no indication that this was dropping off with repeated shots. Now, based on the work we did 2 years ago to modify the theory to take into account the current in the individual filaments and its impact on compression, we developed a new, again, based on fundamental principles, scaling law, which actually goes up as I to the 9th power. And that is not a fit to these dots. That's the theoretical scaling law. And we were able to increase the current in our device by increasing the voltage beyond the plateau region, which we've all encountered in the area of 1 megamp. Given the small number of points, we have to say this is tentative confirmation, but tentative confirmation is that we have gone through the plateau region, and with the filaments being doubled in current, we've reached a new regime of rapid scaling in deuterium yield. We started the Decaborane shots back in November of 24. Now, Decaborane is a solid at room temperature, so we have to heat it to generate the vapor. And we immediately ran into the heating problem that if there were any cold spots anywhere in the device, the Decaborane would precipitate and you couldn't get high pressure. So we basically were able by June to get all parts of the system up to 75 C, which allows a fill pressure over 2 torr. Now, we couldn't just pour on the heat. People might be asking, what's difficult about 75 C? Because our mylar insulation has to be kept below 100 C. So we have to give even heat rather than just unlimited heat. And the way we did that was comprehensive layers of insulation, which you can see in the picture, sort of makes our machine look rather homely, but it does the job. We also optimized the thermocouple placement so we had accurate feedback of what the temperature at various spots really was. We're delivering the heat by electrical heating tape. And then we found that we couldn't get accurate pressure reading unless we used the more expensive heated gauges, which maintain the heat, the temperature of the gauge at a standard 100 C, no matter what the temperature of the gas in the tank is. So that way we could get reliable pressure measures. We were able to put the Decaborane in a transparent glass jar so that we could monitor its state. In this video, you can see it's actually reached the boiling point. It's melted and is boiling. Now, initially we thought this was good, but we realized that when it melts, it can change the polymerizations. It can polymerize, which is not good. So in future experiments, we're keeping the pressure below the triple point so that this boiling, which occurs at about 20 torr, can't occur. The cleaning shots were very important to start getting good results. So when we did no cleaning shots and we had a boron plus deuterium mix, we got no pinch, even with the deuterium present. But once we had the cleaning shots, then we were able to get a pinch with the mix of a small amount of Decaborane with a large amount of deuterium. And we got a small amount of neutrons from the deuterium fusion. After we did the deuterium nitrogen cleaning shots, then we were able to increase the pure deuterium mix by a factor of about 25. So in addition to the factors that I mentioned before, the cleaning was a huge factor, which was lifting our yield from 10 to the 10th all the way up to most shots being well above 10 to the 11th. And we demonstrated that the cleaning shots made a big difference with deuterium. Dr. Hassan suggested that we just do a run with no cleaning shots in between. And you can see that the deuterium yield decayed exponentially without the cleaning shots. We basically interpret this as an accumulation of debris on the beryllium anode. So even though we solved the heating problem and the cleaning problem in part, we still had a big problem, which people were just talking about, is the boron and the hydrogen separated. And we could see basically the problem. The alphane critical velocity acts as a speed limit for boron, but not for deuterium or hydrogen because they're already fully ionized. So basically, at each boron ionization state, there's a pause in the increase in velocity until all the borons are ionized to that state. This is Alfvén's equation. The ionization energy equals 1/2 the kinetic energy. The ionization energy equals the kinetic energy, and you have a pause in the increase in kinetic energy until you get full ionization at that state. So the ionization states of boron are pretty small up until the fourth ionization state, which is one of the two inner electrons, and we want to avoid getting there because we don't have the energy in the rundown to bring all the boron to 259 eV. We only have that energy during the radial compression. So this is basically a speed limit, and we were violating that speed limit. And what we showed was the Decaborane started to deposit on the beryllium, and we were getting these nice, very attractive lines of what we determined was beryllium boride. Now, the problem with beryllium boride is that although it is a weak conductor, it is about 1,000,000 times less conductivity than beryllium. So the current has to cut its way through these beryllium boride deposits, and that is what actually creates these lines. The deposits start just where we expect the velocity to exceed that 1.3 centimeters per microsecond. What we found was that a well-known hydrodynamic instability was creating these lines, these stripes, and the stripes were therefore concentrating the current at the bottom of these grooves. And that concentration of current was unfortunately putting a lot of stress, thermal stress, on the beryllium. So at the end of August, the beryllium anode cracked. And we actually were able to see when we removed it that the crack did indeed start at one of these very narrow grooves between the stripes. So that sort of stopped our experiments. We actually had a spare anode, but it has to be remachined to the same length. And because we had to wait online, we still don't have that anode back. We do have the anode in hand, but we had to have it annealed. The good news is on the very last shot, we got the first pinch with a near pure Decaborane mix. So in the past, we had been getting pinches with a heavy mix of deuterium and a little Decaborane. This was 1.3 torr of Decaborane and 2 torr of deuterium. Now, since the Decaborane is 30 times the mass of deuterium, this meant that by mass you had overwhelmingly the Decaborane. Now, this was too small of a pinch to get measurable fusion with the Decaborane. So we're measuring the fusion through secondary reactions. The Decaborane produces helium, and then the helium nuclei, the alpha particles, react again with the boron 11 to produce carbon 11 and a neutron. Nitrogen and a neutron. And then we can measure the neutrons. but the neutrons are down by a factor of several hundred from the primary reactions. So you have to get a substantial amount of fusion to actually get measurable fusion from these secondary reactions. So we didn't obtain that in this experimental run, but we did get the first sign of decaborane pinching. Now, we still don't think that the hydrogen and decaborane are fully together, but we expect we can do that in the next experimental run. Now, this last shot also gave us the first image of the formation of the filaments early in the rundown with the nearly pure decaborane. We haven't demonstrated that they're lasting, but they are forming. And then finally, we have identified many of the lines, almost all of the lines, in this rather enthusiastic spectrum that we get with the almost pure decaborane. So you see, we identified the beryllium lines, the boron lines, which we had already identified last year, the nitrogen and oxygen lines, and we only have two major lines left unidentified at 625 and 704 nanometers. Now, we don't know exactly what those are. If anybody is getting optical spectra and has noticed these lines, I'd like to hear that. The next steps are, the first goal is getting measurable yield from decaborane. And measurable yield would amount to approximately half a joule total fusion yield. Again, we'll be measuring only the secondary yield. We expect to get the new spare anode installed and baked out by mid-January. Our basic step to getting to that first goal is to prevent the separation of the boron from the hydrogen and the beryllium boron deposition by making sure we get a subcritical rundown velocity. That's going to be a little touchy because, as we say, we know what velocity we want, but we don't know the ratio of that velocity to the alphane velocity with the boron hydrogen mix. So we're probably going to basically run with as much decaborane as we can to make sure that even if the pinch is late after the 1.8 microsecond peak of our current, that we will at all costs avoid this deposition, because beryllium borite is an extremely tough material. It has a hardness that's very close to that of diamond. And we read that the military have been investigating beryllium boron as a armor material. So we suspect that once it's deposited, it will be very difficult to remove it. So our main goal in these first shots in January is to avoid that deposition. The second goal, much more ambitious, we think we can get to 100 joules fusion yield by optimizing the rundown velocity, the cleaning mix, and the axial field, because as Sunil has mentioned, the axial field will exponentially multiply itself. And if we can fine-tune that, we can get an optimal sized plasmoid. And I didn't mention it on the slide, but we'll also be trying to optimize the pre-ionization. During this long pause in our experiment since August, SciAd has used that time to prepare for the upgrade that we intend to do early next year from 8 capacitors to 12 capacitors to obtain 2.4 megamps. And what that involved in was making 8 new switches and 4 new cables. With that full 12 capacitors, our ambitious aim, and we won't say when we will achieve it, is to get net energy out of the device. So thank you very much for your attention.